Nice question here. We're given a 2 by 2 matrix that represents a transformation, given us some properties, and we have to work out what it is. So I'm going to call the matrix A, B, C, D for its elements. And we're told for the first piece of information, the image of the point 0, 1 is the point 3, 4. So that means when we transform 0, 1 by multiplying it by the matrix that we're interested in, T equals, I'll just write it up here, A, B, C, D, then I'm going to get the vector 3, 4, the coordinates 3, 4. So I can actually do this multiplication. I'm going to get A times 0 plus B times 1 is 3. And that means B is just going to be 3, because it's just B equals 3. And then I do the bottom one. I'm going to do C times 0, that's just 0, plus D times 1 equals 4, so D is 4. And I'm on my way. So let's just keep track of it. We've got D equals A, C, 3, 4 so far. Next up, we're told that an object shape whose area is 7 is transformed to an image shape whose area is 35. So that means we're multiplying by 5. That is the scale factor for the enlargement. And what that means is the determinant is equal to 5. Determinant of t equals 5. But I'm not going to prove that here or anything, but that is a fact. So we can say that 4a minus 3c equals 5. I've got myself an equation. And finally, t has a line of invariant points. Okay, well, let's investigate that then. So a3c4 times some point a lot on this line of invariant points. Now, an invariant point is a point which, when you apply the matrix transformation, it stays exactly where it is. But there's a whole line of them, so all of these points will stay the same after we multiply by the matrix, which means we multiply this coordinate x, y, essentially, we write it as a vector, it's going to take us to x, y. Which means when I multiply this out, I'll get ax plus 3y equals x, and cx plus 4y equals y. That means, now don't forget about this up here. But what we then have is that cx is going to equal minus 3y, or actually 3y is going to equal minus cx. And I can sub that in to the first one. So therefore ax minus cx is going to equal x. And this is true along my whole line, so I can divide through by x. It must be that a minus c is equal to 1. Put the two together. 4a minus 3c equals 5. Actually, I'm going to times this one through by 3. Give me 3a minus 3c equals 3. Subtract them. Give me a equals 2. And that must mean that c is equal to 1 if I put it back into this one here. Hence t is going to equal 2, 1. That's my a and my c. 3, 4. Okay, enjoyed that. Now let's take a look at the final couple of parts of this question. Got the transformation S represented by matrix B, given here. We're asked to find the equation, the line of invariant points, and then to show that any line of the form y equals x plus c is an invariant line of S. So let me just talk about the difference between these two ideas. Line of invariant points means we've got a line, and then as we take any point on the line and apply the transformation from B, we'll get back to the actual point, the same point itself. Whereas an invariant line, you've got a point, and you can do a transformation, and it's going to move somewhere else along the line. It's still along the line, it's just they're all kind of moving around. Might be that they all kind of switch signs. They all go from, being up here to down here, negative, for example. Okay, so let's take a look then at the line of invariant points. So this is going to be when 3, 1, 2, 2 applied to, we can see as a position vector x, y, is going to equal the same position vector. That's this here. So then I can multiply the matrix out. I'll get 3x plus y equals x, which means that y is equal to 2x. On the bottom one, I'm going to get 2x plus 2y is equal to y, which again means that y is equal to 2x. So it's consistent, and that is going to be our line of invariant points. Let's put a little box around it. Now for the invariant line. So I'm just going to talk about the general idea. It would be 3, 1, 2, 2 applied to a core of x. And then we're going to have, for our invariant line in general, y equals mx plus c. So you'd write that here, mx plus c, because that will be my value of y that goes with the x. And then we're looking for where that's equal to, so x is then going to go to x dash, some other value of x, but importantly, we're going to get mx dash plus c here. Then it will still be on the same line. It still has the same equation, essentially. Y is going to be mx dash plus c. It's just a different x value to originally. So that's what I'm going to apply here. It's just, I've got a little bit of a helping hand. I'm told that actually show that any line of the form y equals x plus c is an invariant line. So that was just that was a general case. I'm going to cross it out actually. So what I can do is say that x, and then it's going to be x plus c. And what I am trying to get is x dash and x dash plus c is my final answer. So let's see if we can do it. Multiply the matrix out, I'm going to get 3x plus x plus c, and then 2x. Sorry, they look really close together. It's not 22. 2x plus 2x plus 2c. And I can write that as 4x plus c, and then 4x plus c plus c. And I have it in the right form. So x dash is equal to 4x here. What is happening is that, yeah, x is actually transforming to 4x, whilst y is transforming to 4x plus c. So if we had 2, it would go to 8, and then it would be, well, because it's y is equal to x plus c, then my y coordinate would be 2 plus c, and that would go to 8 plus c. It's still on the same line, y equals x plus c. That's the point. That's why it's an invariant line. So I think that's all I need to say, really. As long as I've made it clear that this is equal to this, I think it's good to just make that clear as well. Then we're done.